Hello everyone, this video is going to talk about thin skin calorimeters, which are a relatively cheap and easy way to measure incident heat flux on the surface. So in this image you can see the front view and the back view of a series of thin skin calorimeters that were mounted on a wall above a gas burner that some tests were being done. So the thin skin calorimeters themselves are put together like this. You start with a stainless steel plate or an Inconel plate or something similar with a high high conductivity, and you weld a set of thermocouple wires on the back about a centimeter apart. This is one way to build them, and I'll give some references at the end that talk about some other ways to build them. You take a quarter-inch thick, or a half-inch thick block of either safe wool or K-wool or some other insulating material. You have a small hole through it, and you let the thermocouple wires that you welded to the stainless steel plate go through that hole, and then you have another block of safe wool or K-wool, and you put a second thermocouple between the two blocks of insulation, and then you have a drywall block behind it, and then you put two holes in the stainless steel plate, and you put screws down through the whole assembly to hold the whole structure together. We use two screws, just drywall screws actually, so that they bite into the drywall easily. So we're measuring the temperature in two locations. The temperature of the stainless steel plate and the temperature in the substrate, the insulated substrate. So to calculate the incident heat flux, we're going to use an energy balance. We're going to say, okay, the net heat flux is the incident heat flux times some emissivity plus the convective heat flux plus radiative heat flux plus convective or conductive losses into the surface. So we have the incident heat flux, convective losses from the surface, radiative losses from the surface, and conduction losses into the surface. So if we want to solve for the incident heat flux, so we can rearrange this to solve for Q incident, and then we can generate terms for all of these heat flux terms. Generate equations for all these heat flux terms. So the excuse me. The net heat flux is this equation: the density times specific heat times the thickness of your stainless steel plate times the change in temperature over change in time of the plate. Then the convective heat transfer is going to be your convective heat transfer coefficient times your surface temperature minus your temperature of the gas, the standard convective heat transfer equation. Radiative losses are going to be epsilon sigma T surface to the fourth, and remember this is only losses, so we're not gonna we actually take into account the incident radiation, the incoming radiation in this incident term here, so we won't subtract off the minus the ambient temperature to the fourth, which you would normally do if you're doing a radiative energy balance. And the conductive losses in this scenario, we're gonna assume that there's a contact resistance. We're gonna use that as our calibrating factor. Basically, we're gonna adjust this 1 over HC term to take into account any variation in the material, without doing some type of what do you call it? Numerical analysis of your calibration data. This is one of the simplest and most effective ways to do it that I've seen. So you have your surface temperature, your substrate temperature, 1 over your conductive resistance plus the thickness of your insulation divided by the thermal conductivity. Excuse me. So you input all these terms into your Q incident heat flux equation, and you'll get this equation at the end. So then you want to calibrate these in some known heat flux scenario. So one way to do that is you're in a cone calorimeter. So that's what was done here. We calibrated the thin skin calorimeters at 25 kilowatts, 50 kilowatts, and 75 kilowatts. And so these are temperature profiles of the two thermocouples. So that this dt over dt, change in temperature over change in time term, is important. It's one of the main components of our solution. So we want to be able to calculate the change in temperature over change in time. So we have a 1 Hz record of the surface temperature, the stainless steel, and then the substrate temperature. You can see it's, sorry, I moved the graph. You can see it's lower, but comes up to close to a steady state location. So you can see the surface increases and then reaches a steady state in all three scenarios, though it takes longer as the incident heat flux goes down. And then when we use this equation that we calculate here, the Q incident equation, we can see that we get these heat flux measurements. So they're pretty good. So we're supposed to be getting 25, 50, and 75. So we get, let's say, 28 here, somewhere around 50 at the end, and then somewhere around 70 at the top. So we get a little bit of drift at the top, and don't quite match the heat fluxes exactly, but we get pretty close. So this is a very basic overview of how to build and analyze the data for thin skin calorimeters. For more information, you can look at ASTM E459, or there's a thesis by Jared Alston that's freely available online, room/corner fire calibration data marine composite screening specimens, and he used a number of thin skin calorimeters in his work as well. He used Inconel plates rather than stainless steel, and they were, I believe they were 6x6 blocks. These, I didn't put any dimensions here, but I was using 2-inch by 2-inch square plates, I believe, if I remember correctly. So I hope you found this useful, and have a good day.